Hey, welcome back. Good to see you again. Thanks for joining the channel. Hope you're all well. Today in this part 2 of this Onkyo Integra A-755 Mark II/70, I don't know why they made such a long name. We are going to do some modifications. Last episode we did the repair of the dead phono stage channel. We had one channel dead in the phono section, and we found it was a faulty Hitachi capacitor, blue Hitachi capacitor. Pulled it out, tested it. It was supposed to be 680 nanofarads. It tested out at 1.1 nanofarads, so it considerably dropped and went open. And then I checked some of the other blue capacitors in this thing, and they were also failed as well, so we replaced those. So that's all fixed. Everything should be running 100% on this amplifier. But the owner has been using this in North American Power. Now this amplifier came from Japan originally. It's Japanese, built for the Japanese market. So it is set up to work on 100 volts AC, and that's what it expects to see. But the owner was feeding it 120 volts. Now I highly don't recommend you do that, because it causes a lot of problems when you over voltage equipment, electronics. It causes capacitors to be overvoltaged. Transistors, they can get fed with too much voltage and they'd be out of their range and they could break down. Resistors, they're only, specified to dissipate, like for the example, this one's 2 watts. You could be putting more power into the resistor than you expect, and it could blow them out. Main filter caps, another thing, they're only rated at 50 volts, and if you over voltage your power coming in, you're going to over voltage your main filter caps. So there's a lot of problems that can be caused from feeding it too much voltage. So in this episode, we're going to fix that. We're going to create a different power system for this thing so that it's a little more happier. Alright, so here's our Onkyo, say A755. And it came from the boat from Japan, and it wants to work here in Canada or the United States. It has a 100 volt AC input requirement at 60 Hertz, but our outlet delivers 120 volts AC, and that's North American standard. But if I look, for example, right now, today it's 122 volts, and I've seen this up to 125 many times. So it will go up from 120. Over the years, North American standard used to be 110 volts, and then they upped it to 115 volts, then they upped it to 117 volts, and now they have it at 120 volts. Seems like they want to feed more voltage through the lines, and with that higher voltage, you get more power you'll get more power through your outlet. I think that's the reasoning why, is just to make it a little more efficient. So there's a number of things we can do. The most simplest thing we can do is we can, let's say this is our plug here. Okay, and we have 2 wires coming out. So the first thing we could do is we could add a resistor between the two. Now, we'd have to calculate the value, but whatever value we calculate will be correct for a certain load. This is probably the least desirable method to do this, because what's going to happen is we're going to have a resistance here that's going to drop a voltage, and what we want is a 20 volt drop across this resistor. 120 volts, 20 volt drop, the remainder is 100 volts that's going fed onto the amplifier. That works if you have a constant, steady load. Okay? Now, with an amplifier, the load's going to go up. The more you turn up the volume, the more current it's going to consume, and things are going to go down south quick with this circuit. The more you draw here, this can increase to 30 or 40 volts even, leaving the remainder at 90 or 80 volts. And that's the imbalance. That's probably the worst scenario of how to fix this. It would be using a resistor, because first of all, you're losing all this energy and heat. There's all this heat coming off the resistor. It's inefficient, and it's very poorly regulated. Okay? So we're not going to do that. All right, so the next thing we could do is we could get a step-down transformer. So get an iron core transformer. And we would have, on this side, we would have a winding wound for 120 volts. And on this side, we would have a winding that's wound for 100 volts. So it's a turns ratio. So we got a turns ratio of 12 to 10. Simplifies it. Now this is probably the next best solution, because this will provide us with 100 volts, and this is actually providing us with isolation too. Not that we need it, because there's already a transformer inside here that will provide us with isolation. Problem with this is power. Transformers that need to deliver the amount of power have to have a certain size. So you can't use a small transformer, because it will run out of steam, let's say, when it gets to even a moderate load. And if you start turning up the volume, you're going to get a higher and higher load. And this is going to even regulate less. It's going to, the regulation on this is fairly poor, because you're going to have losses. You're going to have losses with IR losses. IR losses is the resistance of this winding and the resistance of this winding, and just the current flowing through it. That's going to be your IR losses. And you're going to have hysteresis losses, the losses of when the magnetic field changes every 60 times a second. The magnetic field changes. You're going to have losses in the magnetic core. You're going to have eddy current losses, and that's losses within the steel core itself, within the laminations. So even though this is better than resistors, it still has a high amount of losses, and it's really not regulated that great. So it'll perform better than the resistor will perform, and it'll be more efficient than the resistor, but this will also give off heat as it warms up. Because when you start putting this to full load here, and this is under full load, things start getting hot inside the transformer. So that's another option. Now this transformer can be external, or it could be built into the amplifier itself if there's room. I doubt there is room. So it would have to be a box that's external, and it has to be a fairly big size too, because this transformer is going to have a lot of iron in it. It's going to have a lot of copper and a lot of weight and a lot of size. So they do make transformers like this for changing the voltage from 120 to 100 volts for Japanese equipment, but they are expensive and they're heavy and they're not easy to come by. I'm going to go look and see if I can find any. Here's a quick look at what's on Amazon for step-down transformers. This one here is 1,000 watts. It says it's 1,000 watts power converter. 120 volts to 100 volts step-down. This one's probably switch mode supply inside there, and for 1,000 watts the size, I'm not sure. So they want $100 and then shipping on top of that. This one here, this black one, this would be more typical of the kind you would need. It plugs into regular 120 volts, and then you plug your 100 volt appliance into this socket here. And this one says it converts step up, step down, converts to 100 volts or 110 volts, vice versa. 500 watts. Now it says 500 watts, but I don't believe that 500 watts. 500 watts is a lot of power, and if you put 500 watts through this, it would probably go up in a puff of smoke. 500 watts, they're talking about surge power. So this one's $43.70 plus another $40 shipping, so it's 80 some bucks shipped to your house. Let's have a look at it. So you get different wattages. 200 watts is the smallest, 500, 1,000, 2,000, 3,000, 5,000. It goes up from there. But they also have disclaimers. This Continuous use of the transformer is capable of both up and down voltage conversions for Japan and USA electricity, and enable the use of Japan products. Okay, 500 watts is the maximum capacity of this transformer, including the power surge, right? So they're probably fusing it for 500 watts. It converts 110, 120 into 100 volts and 1 volt, 100 volts backup. Means it can convert both ways. On-off switch and fuse for safety. And then it says here, it says remember to leave at least 100% margin for power surges spike when buying transformer. For power tools, laser printers, heating appliances like rice cookers, coffee makers, so blah blah blah, you must leave a power spike margin of 4 times. So actually what they're saying is you can only use this for about 125 watts, even though it's rated for 500. So yeah. And the problem with these, if you put heavy loads on them for extended periods of time, they will overheat, and the thermal fuse will either blow out or they'll smoke. So you have to be very careful with these. So for the Onkyo amplifier, this would probably be fine, but I wouldn't run the Onkyo at full power with this, because this would probably overheat. Even though we're dealing with a 35 watt per channel amplifier. So you can buy them. They're kind of expensive, and yeah, they work. But then you have an extra appliance that's sitting on the shelf beside your amplifier. So probably the next best option would be an auto transformer. And an auto transformer is like a transformer, but it's not. It's you still have your iron core, but you only have one winding instead of two. Now, the way they wind an auto transformer is 120 volts coming in, so they'll wind one coil for 120 volts, and then they connect it up, and then your load is tapped off on somewhere along the line here, somewhere up here. So you can feed 120 volts in here and get 100 volts out here, depending on where you place your tap. And this is the same principle on how a variac works. A variac is a variable transformer that has a slider that runs along the coil, and it goes from 0 all the way up to, actually it goes beyond the 120 volts, and you can get like 140 volts output if you want. That's what a variac will do. But we're not going to use a variac. They're pretty heavy and expensive, and they're inefficient. And yeah, so trying to find an auto transformer with the correct, you probably could find them. I don't know. I haven't seen them out. You'd probably have to get one custom wound. And this would probably be a little smaller than the regular transformers, because you're dealing with one less winding, so they have a smaller physical size, and they might be sized small enough to fit inside the amplifier, but I kind of highly doubt it. So that's another option. So what I forgot to mention is, probably with the auto transformer, you're probably going to have better regulation than just a regular transformer. So that's the positive there. But for the final option, the one I'm going to do is I'm going to install a buck transformer. So what's a buck transformer? Well, a buck transformer is a transformer that's placed in the circuit to oppose the line voltage to drop it. So here, I'll show you how it's set up. So we have our voltage here. Let's have our transformer here. And this winding is our secondary. Okay. So let's wire this up for the purpose of buck. Now, what we're doing here is we have 120 volts coming in. This is a 120 volt transformer. On the output, the secondary is rated at 15 to 18 volts. And what happens here is this is wired in the opposite phase of this. So as 120 volts comes in, it's opposed by 15 volts of out of phase voltage, and that drops this down to 102 to 105 volts, right? That's in theory. In practice, it's different because we have to call our IR losses, and we're going to have other losses within this too. So the advantage of this one is we don't need a full-size transformer to carry the whole 100, 200 watts that this amplifier needs. We only need a transformer sized to carry the portion of the load that we want to remove. I don't know if that makes sense to you. Let me show you the transformer. So here's a transformer that I ordered for the Onkyo as a buck transformer. Packaging here. Just came the other day. Comes with all this stuff. Oh, these little rockers. And got a mounting plate. So this is what I purchased. This is a 50 volt amp transformer, and primary is 110 volts, secondary is 118 volts. So now this might be too much voltage. I might have, in hindsight, I probably should have got a 15 volt, but we're going to try this and see how it works. I don't need to use this mounting plate, I can make my own. And then, let's see here, red is primary, blue secondary. Okay. Now this is small enough that I can just mount inside the receiver or the amplifier, and we can wire it, configure it to have a buck, to buck the voltage, so that as 120 volts comes in, we put our buck transformer in, it's going to reduce it by this 15 to 18 volts, and then what we're left with is hopefully 100 volts that we can feed into the internal power transformer. Now, why did I select 50 volt amps? Actually, they sold this as a 50 watt transformer. Watts and volt amps are similar, but they're not the same. They're different. Okay, so first thing we should do maybe is we should test this transformer, put 120 volts into it, and see what we're going to get out. This thing's, it says it's wound for 110, but I'm going to be feeding it 120, 122 right now. So it's going to be over voltage. That's why I think I should have went with a 15 volt transformer instead of an 18, but we'll see how this works. So let's hook this up to power and we'll see what we have for a true reading on the secondary. Okay, I got my Widowmaker here. Let's hook it up to the primary. And let's power this up. Make sure that we're safe, no shorts. Power this up, and there it is on idle, consuming 1.1 watts, and on our output we should have 19.5. Okay, so let's write that down, 19.5. 122 volts. Okay. So if we do a little bit of math, 122 minus 19.5, that should give us an output line voltage of 102 volts. 102.5 volts for the Onkyo. That should be good. But there's more to it than that. When we start loading this down, we're going to start seeing how this is going to change. So let's do some math on that as well. So what I did is I took this and I measured on my HP, what is it, an HP 3468B, 6-digit multimeter, or 5-digit, I can't remember. And it came out with 395 milliohms, which is probably accurate because I used the 4-wire sense reading probes. So that's probably more accurate than the 600 millivolts of my crappy old meter there. So let's use the 395 milliohms for our calculations. Now at idle, idle we're going to have for 98 volts input, we had 17 watts draw at 240 milliamps, 240 milliamps, and 0.75 power factor. Okay, power factors, we're not going to get into power factors too much here because it gets complicated. And I used to be able to know how to do all these calculations when I was back in school, but I long forgot it all. So at idle, this is sitting in, it's drawing 240 milliamps. So our voltage drop across the buck transformer at idle should be R equals E times I. Is that how it goes? So we have 0.395 times 0.24. We should be getting .94 millivolt drop. Across this transformer. Loss. That's a loss. That's a negative. That's a loss. That's ER losses. Okay. Now, if we have full load was 145 watts, 1.73 amps, and power factor was 84%. Okay. So if we do the math on this one as well, 1.73 times 0.395. Actually, it's better than I thought. So we should be getting 683 millivolts loss, and that's ER losses. So this is going to actually work out pretty good. It's going to be fairly well regulated, and it should work out. We're going to put this in and give her a try. I need to figure out a mounting for it though, and I think this bracket's going to hit the garbage. It's all bent anyway, but see how it's bent from shipping, but you could straighten that. The quality of the transformer is really nice. It comes with a mount, it comes with a bolt, but I'm going to have to figure out a different mounting for this. And in case you were wondering, this secondary should be good for several amps. We have a 50 volt amp transformer and it's delivering 18 volts. So if you just do the simple resistive load 50 divided by 18, it comes back with 2.77 amps at full load on a resistive load, non-reactive. And we are still well within our limit here. We're asking for 1.73 amps, and this thing will deliver 2.7 amps. So this is rated, I think it's correctly rated. I wouldn't go smaller because then you lose your regulation. It won't regulate as well. So I don't know what else to tell you about this. Let's hook it up and see how it works. So for this Onkyo, I'm planning on mounting this transformer right on top of the other one, and there's plenty of room for it. We've got lots of height, and the height is good. Probably what I'm going to do is I'm going to custom make a bracket that fits over top of the two bolts on top here, and so that gives me something to mount to. I'm really out of options as far as room here. I can't put it over here because this is all full with wires, and there is room for it here, but that would be really a tight squeeze, and then I have to figure out how to mount it. I think the best thing is mount it right here with the other transformer, and I'll have to make up a special bracket. I'll have to ditch this bracket and get us another one made up. So I'll take some measurements. I wonder if I can modify this bracket to fit. Because it already has the dimple in the hole for the bolt. It would be an ideal thing if I could just modify this one to fit. Might have to cut it and fold it over, but it's got these slots. I don't know if I can make it work. I'll see what I can do here. I gotta relocate some of these wires too because they're almost in the way. And they don't have a lot of length to them. I can push them out of the way like this. There. Yeah, I think that's the solution right here. I could make, well, I'll think about this. I've got lots of options, but that's where it's going to rest. Okay, I think I got this figured out. What I'm going to do is I'm going to make two U-shaped pieces that fit over top of the transformer. It's going to start from about 20 millimeters down from the top. It's going to go up, across, and down. And it's just going to be like a bracket or a, yeah, just a bracket. And it's just going to fit over top, and it's going to be hold so that this bolt can bolt it down. It's going to have a nut on the end. And I'm going to make two of those. It's going to be a strip about this wide, and it's just going to be a hole here, folded, another hole. It just goes, wraps around. And then what I'm going to do after I get those two is I'm going to take this piece, probably, get rid of that. Probably what I'm going to do is I'm going to cut this piece right down here and right down there. Just get rid of the ears. And I can spot weld the two pieces together. Just put a couple, 3 spot welds here, a couple of spot welds there, and then that will be permanently fixed to those two brackets. And then this is the bottom of the transformer bracket, and it's going to be narrower. Don't know. Might cut in. That's what I'm worried about. I got the rubber washer here. This came with this, so it shouldn't cut in if I put this like so. I want it securely mounted so that if this unit ever gets dropped or something, this won't budge. So it's going to be like that. All right. Okay, after a little bit of cutting and fitting and trimming, and so there's my two brackets. They're in place. They're drilled. They will accept the, I think these are M5, maybe they're M4. They accept the screws, so it's all good. My next step is I'm going to trim this. I don't know if you see that line. I'm going to cut it along that line and just cut it into a disc and get rid of the square part. And then that'll sit right on top, and we'll have to spot weld that. But the trick here is going to be locating it so that it doesn't, yeah, holding it and locating it while I have it spot welded so it's not out of position. That's going to be the difficult part. So, got that part's done. Let's cut this now. I'm going to take that to the shear and cut it in a circle and get this finished. Okay, so here it is. This is the bracket I made. I took the original bracket that came with, cut it into a circle, and welded on two other sheet metal brackets. This is all made of steel. This is probably the hardest part of the modification. It was just getting this to have a location to mount. So that's going to go there, and it's going to get bolted through. Now, word of caution, these screws, and you see they have insulating washers on them, and there's a reason for that, because these screws are going through the core and they need to be insulated. You can't have a circuit with a short circuit here, because it will act like a shorted turn, and it'll use up the energy that's being converted into magnetism. It will cause eddy losses, and if you try and imagine this as a shorted turn, you might get a fraction of a volt, but you could have several amps flowing through here, right? And it would start to heat up and cause your transformer efficiency to go way down, and that's not what we want. So we want to keep this insulated on one side So what I'm going to do is I'm going to add some electrical tape to cover these surfaces so that they can't short out on this, because these are actually would be a shorted turn as well. Okay, here's a look of how the amplifier is wired currently. It has an unswitched outlet, a switch with a bypass capacitor, two switched outlets, 3 amp fuse, and it goes to transformer winding. It's pretty basic. Here's what I propose. I'm going to break the connection here, and we'll install our transformer here. And of course we're going to have to wire this so it's out of phase, so it bucks to 120 volts. And here we should have about 100 volts. That's the plan. Now if we wired this into a boost configuration, we have to be careful here, because we could actually do this as a boost, and this would be over 140 volts here, which we don't want going into a 100 volt transformer. So we don't want that, we want this. So let me get started. We're going to have to reassess this 3 amp fuse, because this buck configuration will actually consume current, because it's going to be reacting and pushing against the voltages going through here. So this, what did I measure right now? I measured at idle. At idle, this is what was it again? 240 milliamps, and at full load, it was at 1.73 amps. So I expect with this here bucking the voltage, I expect this full load here to be higher, probably over 2 amps somewhere. So like I said, we might have to revisit this fuse and put a different size in. Okay, just one last sanity check before I close this all up. This is should be my 100 volt line, and this is my input for the transformer. These two get tied together, but before I want to measure the voltage on this just to make sure that we are at 100 volts. So let's plug this in. Where's the power cord? And just test this before we close it up. Okay, going on. And there we go, 103 volts. Should be good. If we make the connection, it stays at 103 volts, 102. So we'll tie that up, and that's going to be our buck transformer. So there it is, it's all installed. I'm going to run some tests on it. I'm going to have this running for a while. It's up around 21.8 watts from 17, so we're consuming, I don't know, 3 or 4 more watts than usual. I just want to make sure that nothing overheats. I don't think it will, not at 21 watts. I don't think this is going to overheat at all. So I'm going to run some tests. I'm going to finish assembling this, and then we can do some full power tests and make sure it's running good. Alright, so I got it assembled a little more than what it was. I'm going to turn this on, not feeding it any signal. What I want to do is I want to check DC offset, because there is adjustments for it on the boards here. Another thing is, one of my viewers gave me some good information on these amps. He says he's got one in Denmark, and after watching the video he went and checked his blue Hitachi capacitors, and yeah, they are failing for him too. So it's probably a common thing for those capacitors. Let's try this here. Got one channel. And what do we got here? 75 millivolts, 7.5 millivolts. That's totally acceptable. We are turned on. Okay, let's check the other channel. 2.6 volts, millivolts. That's good. Now let's check the bias setting. There is a couple probes here, test points I can clip onto. And we've got 7 millivolts there. Let's try the other channel. 2.4 millivolts. We can adjust this one up, I think. This one might be the zero adjustment. Let's try this one. It's a heavy conduction. Okay, there we go, 7.3. Now I think I screwed up the zero on this one. Let's try adjusting this again. I really don't like adjusting amplifiers blind. Okay, 4.7 that one. 5.3 on that one. I'm just going to leave those alone. Alright, so I'm all wired in to do another power test here. Basically what I want to test is monitor the voltage of the AC going into the original Onkyo power transformer. And this voltmeter here will tell us what it is. And then I have my watt meter here. We're going to watch that as well. Switch this thing on. And so this is a voltage going in, 122. This is the voltage coming out, 102 from this buck transformer. So let's turn up the volume on the signal. I have to set this for tuner first. Where's my... that is right. Yeah, here we go. Okay, here we go. And I'm going to take it up. I got it on 8 ohm load. I think I'm going to take it right up to full power. Let's see what we're at here now. We're only at 6 volts. So let's keep going. Let me see, I might have to change my scale here. Let's go up. Here's clipping. Full power. So, 100 volts going in from 102. We only dropped 2%. That's very good for stability, actually. If you go from 0 idle, 2.2, 2.1 to full power, you only lost 2% of your voltage, which is good. So let's get this up to full power. So we're at 170 watts here, 1.7 amps, 82% power factor. Everything looks really good. I'm really pleased with this. I was hoping it wasn't going to sag too much, but it's really holding up. This buck transformer is probably the correct size for this amplifier. If you're, what are we at right now? We're at 17.90 volts RMS on the output. So, if you do the figure calculations, I think an adequate size buck transformer would be around 35 volt amps or so. But since we got a 50, we have extra headroom. So this thing's ready to go, and it's ready to perform. So you can plug it into 120 volts now, and internally it corrects the voltage to 102, and it's fairly stable. It's more stable than I actually thought it would be, so that is a good thing. Yeah, all that's left to do now is disconnect everything and put it in for listening tests. I like your stimulus. So that's it for this one. Just came in for the repair, the dead channel phono, and we found one of these capacitors that failed, and then we checked the other 3 and they failed as well. And like I said, since I released the last video, the comments came back. I had one comment from one of these Onkyo owners that says, yeah, he checked his and caps are bad. So it's a systemic failure of these Hitachi caps. If you see them in circuit, be very suspicious of them. And that transistor that was floating around the bottom, that was just from the previous tech. He probably dropped it in there and lost it and then forgotten about it. But it's all good now. It's working good, and I'm going to enjoy listening to this one for a while. So just a few words about the power transformer, the buck transformer conversion. That transformer cost me $53, I think it was, shipped to my house. Now, you're going to go online, if you go to Aliexpress and look up 50 volt amp transformers like that, you're going to see a wide range of prices, with shipping, without shipping. I think they're all basically the same price, $50 Canadian. What are you looking at, $35 US? So I think that's a really good, cost-effective way to convert Japanese-born equipment to work in North America. And as you saw, it works great. Voltage line regulation is within 2%. So I think it was a success. Result. That's my word, result. One other thing I forgot to mention, and I still need to do it after I finish this video, is I need to make up a tag that says converted to 120 volts AC, and I'm going to put that on the bottom of the amplifier, just so that if he wants to sell this or gift it to somebody, then they know it's already converted to 120 volts. Now, the owner was also questioning me about safety of this. Well, as you can see, it really doesn't consume any more current. It's still at 1.7 amps at full power, and there is no need to change the fuse because we're still using the same 3 amp fuse. And as far as safety goes, there's really nothing to go wrong with this circuit. It's just a matter of adding another transformer in series with the other one and making sure the connections are all insulated properly and tucked away. This is fully reversible. This can be pulled out and put back to factory spec really easily by anybody that's competent in working on these. I'm sure they could figure out how to wire up the primary side of the mains input. But if for whatever reason, if they wanted to convert back to have this back to 100 volts, they could remove that buck transformer easy enough, and there's no scarring, there's no parts I cut out and are missing now, so it's all there. It's just what I added to the circuits. Thanks for watching, take care, and we'll see you on the next one, and I hope you're all well.